shut down the devices and laptops. Let me start with some announcements. There is a midterm exam this week, as you are all aware. It's going to be on Thursday. And just to help with any last minute questions, I'm going to have extra office hours on Wednesday. Okay? So right after Wednesday's lecture, anyone can stop by if you have last minute questions or anything like that. Okay, so that's the first announcement. Second announcement is some people have been asking for solutions to homework 3, which is really a practice exam from last time. I will try to post those today. Okay, that way if you have any questions about exam questions from last time, you can look at the solutions. All right. Okay. The third announcement was, I think I clarified this on Piazza. Some of you asked what's the material that's going to be covered for the test. Okay, so it's going to be lectures 1 through 13. Everything we did until spring break is on the test. What I will do today and Wednesday won't be on this test, that will be part of the final exam. Okay? This is just so that you don't have to take last minute class material and study for the test. So if you just focus on lectures 1 through 13, you should be good for the rest. Okay? Any questions about the exam before I proceed with the lecture? Logistic questions or anything like that? All right, so let's start. So before we broke for spring break, we were talking about distributed snapshots. Okay, so I presume that you have reviewed that material over the break and we'll continue from that point on. So today I'll talk about a new problem called termination detection that can be solved directly using our distributed snapshot algorithm we talked about last time. Then for the much of the class I'm going to talk about 2 techniques, leader election and mutual exclusion. Okay, leader election is something you might have to use in your lab. So it's material that you should be familiar with. Mutual exclusion is just the problem of how do you implement a distributed lock. Okay? You probably all know how locks work, you know how they work in a centralized setting. You have a set of distributed processes or applications that need to use locking. How do you go about implementing it? So that's what we will focus on. Okay, so let me start with a quick recap of distributed snapshot. So if you remember, the problem of distributed snapshot is one where we want a set of processes that do not have a global clock to take a snapshot, which means they need to checkpoint their state and they need to checkpoint all the messages in transit. Okay? The reason we have this algorithm is if any one of the processes crash, rather than terminating all the remaining processes and starting the computation from the beginning, you can simply terminate the processes and start them from the most recent checkpoint. This allows you to not waste all of the computation cycles that have been used up so far. Okay? So that was the distributed snapshot algorithm, and the main takeaway there is every process needs to save its local state, which is in-memory state, and you need to checkpoint all the messages in transit, which are all the messages queued up in socket buffers. Okay? And we looked at how to do that. I'm going to continue from that point on and talk about termination detection. Okay, so let's assume that every once in a while your processes are checking a checkpoint. Okay? You also want to answer the question whether all the processes in the aggregate have finished the computation and there is nothing left to do. Okay? If there isn't anything left to do, the processes can then gracefully terminate themselves, and then the whole application will shut down. Okay? So this is an example of, let's say, distributed simulation. Each process is doing some local part of the simulation. They're exchanging messages. You need to know whether the process needs to know whether it can finish. Okay? And the notion of whether the distributed computation is done is as follows. Okay? We'll say the entire computation is finished if every process in the computation has finished all the work that was assigned to it. Okay? And there are no messages in transit. Okay? If there are any outstanding messages in transit that haven't been processed, a process that receives those messages might actually do something else. Okay? So it would not be done. Okay? So we will say that the computation is terminated, okay, if and only if all local processes are finished, there is no outstanding work, okay, and there are no messages in transit. Okay? So if that is the case, that means that there will not be any more work for any process to do. Okay, if there's any process that is still computing, then obviously the application still needs to continue to run. Okay? Or if there are any messages in transit, also processes need to continue to run to process those messages and take some action based on the message, okay? Which might trigger yet more messages. Okay? So what we will now do is basically look at the snapshot algorithm and just use it to figure out when the computation is done. And the process is very straightforward. It's simply a query that is going to go through your entire distributed set of applications, and then you collect responses and figure out what is actually happening. Okay, so we will assume, okay, that in addition to our marker process or marker packet rather, that was being used to checkpoint state, we'll have two more types of packets. Okay? A done packet and a continue packet. Okay? A done packet says that I'm done. Okay? That means I'm locally, I have nothing, no more work to do. Okay? Continue basically says that either I or someone that I'm interacting with is not done, so that we have yet more work to do. Okay? So these are the two messages we'll add to the protocol we studied last time. Okay? And essentially what we are going to do is any process that also starts the computation can also send a query saying, tell me whether you're done or you wish to continue. Okay? And then when a process actually receives the marker message, it is going to send the same query messages out to its neighbor saying, are you done or do you wish to finish? Okay? Now when you have sent these messages, you are going to wait for a reply. Okay? If all the replies come back to you saying your neighbors are all done, okay? If your neighbors are done and you are done, then you are going to send a done back to your ancestor that sent you that marker message for the snapshot. Okay? If any of your neighbors tell you that they wish to continue because they still are not done with their computation, they have some messages that they need to process or any of those reasons, okay, so if you get a continue message from any of your neighbors, you are going to send a continue message. Okay? So essentially you are querying the network to figure out if every process is done or not. Any process that's not done will cause a continue message to trickle back, and then processes will just still continue to run. Okay? If everyone says they are done and the process that initiated the computation finds out that all processes say they are done, which means that they're locally, there is no work to do, there are no outstanding messages, then it can send a message saying terminate because everyone is actually done. Okay? So it's a simple query protocol that is layered on top of our distributed snapshot algorithm. Okay? That is essentially going to also figure out whether processes are done or not. So here is the rules that I said. Essentially you will send a done if all of a queue is going to send a done message to its parent or ancestor if all of its successors send it a done message and it hasn't got any outstanding. So no outstanding messages, all your neighbors are done, you send a done. Otherwise you will send a continue, which means if any of your neighbors have sent your continue or if you have outstanding messages, then you are going to say that there's still work to be done. Okay? So simple idea, but it's something that actually layers easily on top of your distributed snapshot algorithm. Any questions on this? Okay? This was just leftover slide from last time. For the rest of this class, I'm going to talk about leader election and then distributed locking. Okay, so let's move on and talk about election algorithms. So this is a new subtopic in the sequence. So first let me explain what is the problem of leader election. Okay, so let's assume that there are a set of processes that want to achieve some task, and let's say the task needs a coordinator process. Okay. Now there are two ways you can decide which process or which machine is going to be the coordinator. First one is manual. Okay. Either the application designer, the programmer, the application designer, or the system administrator says this is the coordinator process of the coordinator machine. That's one way to do it. Okay. The other way which we are going to look at here is the processes themselves elect a distinguished node, okay, or a node that is going to become distinguished and say that's the leader. Okay, and that's going to do whatever task you're trying to achieve. And we have seen a number of techniques already where you need a coordinator or a leader process. If you go back to clock synchronization, okay, we needed a master process. Okay, that was basically the time server. Okay, so you could say, should the time server process be decided by the user, in which case that's manually done, or should the processes themselves elect a leader? Okay? If you want to do the latter, then you have to use the election algorithm to figure out who's the leader. Okay? When we talked about Skype or peer-to-peer processes, we talked about this notion of a super peer. Okay? And I mentioned in that context that super peers will often be elected by the group of peers that want to have a coordinating process. Okay? Again, you'll have to use some sort of a leader election technique to achieve that. Okay? So, and there will be many other scenarios where we will see that there is a coordinator or a leader. Okay? All of those techniques are going to ride on essentially an election algorithm that's running underneath it. Okay? Because you will essentially need to elect a leader. If the leader crashes, you will have to detect that the leader has crashed and elect a new leader. Okay, so it's basically a dynamic thing. It's not that once you have a leader, that's the process that's going to be the leader forever. The leader can quit, leaders can crash. You will have to then rerun the election algorithm and elect a new leader. Okay, so that's basically what is the problem of leader election. Okay, and I talked about the Berkeley clock synchronization already. So I'm going to show you two different techniques to do this. First is called the Bully algorithm, the other is called the ring algorithm. Okay, let me start with the first one, which is a Bully algorithm. Okay? And these are the simplest forms of election algorithm. There are many, many variants of this that you can actually read about in papers and so on. I'm going to actually only show you two very simple ones, which is adequate to get more simple tasks done. Okay? So in this case, what's going to happen is all the processes that you have, let's say there are n processes, and you want to elect a leader. Okay? We are simply going to assign a unique numeric ID to every process. Let's say we just number the processes 1 through n. Okay? And then we'll say we want to now run a leader election. Our simplest way to do leader election is to say that the highest numbered process is going to become a leader. Okay? So of all the processes that are still alive, okay, the process that has the highest ID is going to get elected as the leader. Okay? This is the simplest form of leader election that does not actually look at the characteristic of the node. You don't say, is that node heavily loaded? Does it actually have the resources to be the leader? You're not looking at any of that. Typically, you might say a leader process should have adequate bandwidth. It should be running on a powerful machine so it can do some extra work of being a leader. We are not looking at any of that. We are simply saying we'll use numeric ID to elect a leader. And we'll see how to modify that to use other characteristics. Okay. So in this case, we are going to assume that processes know their own IDs and the IDs of every other process. Okay. We'll just make that assumption. It's a simplification, so let's assume that. We'll also assume that communication is reliable. Messages are not going to get lost. We can just assume that you're using TCP/IP, in which case we just get that property for free. Okay? And in this case, our ideas we have to find the process with the highest ID. And the way we are going to do this is we are going to run something called an election. Okay? We're going to elect a leader. And the way we are going to elect a leader is we are going to query saying who is the highest order process, and then if that process says I have this ID, that's the one that's going to win. Okay? And so the way this works is, let's say the current leader, whatever it was, has failed, or you just started a new application that wants to elect a leader. Okay, so any process in the system can initiate the election algorithm. If you see that the current process has failed, any process can say, let's elect a new leader. I don't see the process that's the leader responding. Okay, so, and then we still want to make sure we actually elect the one with the highest ID. Okay? There will be three types of messages we will have to consider. There's an election message, okay, there's an OK message, and there's an I1 message. Okay, and we'll see how the processes work. So let me show you an example. We will see that it's order n square. Okay. So essentially what happens is when a process decides to run an election, it is going to essentially send an election message to all processes that have an ID higher than it. Okay. So if say you are process I, you want to learn a leader election algorithm, the goal of which is to find the highest ID process that will become the leader. Okay, so process I just needs to find if there's any process which is greater than I that's still alive, you know that process will win. Because by our rule, the highest ID process essentially becomes the leader. So all it has to do is it has to send messages to all processes with ID I plus 1 through n, saying, let's elect a leader. If any of those processes respond to you, you drop out, saying that there's a higher ID process, you can figure it out who the leader is. Okay? And then this will recursively continue. all the highest ID processes will then essentially try to figure out who is the highest ID process among themselves and so on until one process is left. Okay, so in each round, okay, some processes will drop out as soon as they see that there are higher ID processes that are alive, and so you go and figure out which among you is the highest one, okay, and then eventually you will be only left with one. Okay, so here's an example to show how this is going to work. So let's assume in this case there are 8 processes numbered 0 through 7. Okay, and then let's say that 7 was the leader and it crashed. Okay, so the next year 4 figures out that there is no, the current leader is not responding. So it decides to run a leader election algorithm. Okay, so it's going to send a message through 5, 6, and 7 saying let's have an election. Those are your election messages. Okay. Now 5 and 6, which are still up, are going to send an OK message to 4 saying that that's mostly to say that here's an acknowledgement to your election message, and it also tells 4 that 5 and 6 are still up and running. So they basically, that OK message serves 2 purposes. It's an acknowledgement, and it also tells you there's at least one higher ID process that's still up. Okay? So 4 is going to drop out saying, you guys figure it out. Okay, so now 5 and 6 will run an election. Okay, algorithm, in this case you see that 5 has run an election by sending message to 6 and 7. 6 also has started an election recursively by sending a message to 7, which is the only highest ID process greater than it. Okay? And 7 is obviously crashed. So what is going to happen now is, as a result of that, 6 is going to send a message to 5 saying I am still up, an OK message. 5 drops out. 6, which ran an election by contacting 7, does not hear back from 7. So it is going to declare itself the winner. Okay, so essentially it's going to then send I1 or a coordinator message to all the processes saying I am the new leader. Okay. It's a very simple recursive algorithm that causes lower ID processes to keep dropping out until there's only one process remaining which declares itself the leader. Okay. Now at some later point, 7 might restart. The machine might be rebooted, or you might restart the process, and then 7 could, if 7 hears from 6 and figures that it has a higher ID process, it can start an election as well and take over the responsibility that it had relinquished when it crashed. That is perfectly fine. Okay, but at this point in time, 6 is the highest ID process, so it will function as the lead. Okay, if at some later point in time 7 comes back up, you can redo this, and then 7 will become the new leader and take over from 6. Okay, yes,
is it a requirement when 7 comes back that it initiates a new election, or is it okay with 6 remaining?
So the question is it a requirement that when 7 comes up, it runs an election algorithm, or is it okay to have 6 as the leader? Okay? There are 2 ways to answer the question. Okay? One is from a pure leader election perspective, okay, you want only one property, which is at any point there should be only one leader, okay, which means you should neither have no leaders or you shouldn't have 2 leaders. Okay? So 7 should not come back up and I was previously the leader, so I'm now going to just become the leader again without running an election. That's bad because 6 and 7 will be both thinking they are leader. Okay? That's not allowed. Neither should we have a case where there was no leader, which is what happened when 7 crashed. Okay? From that perspective, if 7 comes back up and finds that there is a leader, it's fine to say that let 6 continue. Okay? But now if someone else at some later point initiates a leader election algorithm, 7 will win at that point. Okay? But 7 does not have to run an election algorithm. Okay, yes.
How does 7 know that 6 is the leader?
How does 7 know that 6 is the leader? At this point in time, these processes have crashed. Processes that have crashed have no way of knowing who the new leader is. Other processes will know. Okay? So when any process boots up, okay, we have assumed here, if you go back here, we say that our processes know each other's ID. Okay? So you can basically, if you just restart it, you can just ask any process in the system who is the current leader. Okay? Because you won't know who it is, but you can ask, and since the other processes know, they can tell you.
Or it will just become the leader, because it will flood to nobody, because 7 has no higher IDs, and it will just send a coordinator message to 6 and will.
Right. So the point that is being made is if 7 comes up, can it run a new election? So I did say that any process can start any leader election at any time. Okay? So if 7 starts up, it could say, I want to take over, and it could run a leader election algorithm. and there is no other process higher than it, so it will automatically get involved in running leader election and taking more responsibility. You could just ask some other process. So let's say it was not 7 that had crashed, but maybe 4 had crashed. 4 comes back, it can still ask someone else and say who's the lead. Okay, so that's also allowed. Yes,
So
question?
what about a system like which is more dynamic, processes are joining and leaving and IDs are being assigned to them, like again and again. So what happens then? Like there won't be, there will be too much traffic of leader election algorithm and all.
Okay, so question is that's being asked is what happens if you have a highly dynamic system where machines come and go. Okay, examples of such systems are peer-to-peer systems where we assume that peers can come and leave at any time. Not every system will have lots of dynamics. Okay? And in the most systems, the only dynamic is actual failure. Okay? And that is what we saw here. But of course, you have other kinds of system where peers just simply enter and leave. They are not failing, they are just departing the system. In that case, there may be too many dynamics. So it's not the case that this election algorithm will be sufficient or adequate to meet the needs of all kinds of scenarios. If you have dynamic systems, okay, you may want to take into account not just a process with the highest ID, but you could say the process that's been the most stable wins, or the process that has the highest resources wins. Okay? You can just change the metric. Here the metric was the highest ID process. You could have said process with the least load. You could have said process that is the most stable, which means that it's going to stay in the system for the longest time. You can use any other metric. Okay? Here we just picked a simple one, but that's not what you should always use. So yes, question there?
So here 4 did not send a message to 0, 1, 2, 3. So can we say that 4 has a global view of the system right now?
Yes, so question was 4 did not send a message to 0 to 3. Does 4 know every other system? So in this case, the reason you didn't send to lower ID processes is you already have a higher ID than those. So they are not going to win by definition. Here you are simply trying to figure out who should be the leader. Okay, and furthermore, for simplicity, we have assumed that the address of every other process is known. Okay? Which means you have a global view. In a very large system, that's not a practical assumption. If you have 10,000 nodes, you're not going to assume I know every node in the system and whatnot. Okay, but for this simple algorithm, you can make that assumption.
So
Okay?
because in this case, then you could just have 4 choose the leader.
Yes, so any process that starts that leader election only talks to the processes with IDs higher than them. Because you know that there's no point talking to anyone lower, you can win by definition. But that's a rule. So there's no reason to communicate with any process with a lower ID. Only communicate with processes with a higher ID in this case.
I just meant that if you already have a global view of the system and you're starting the leader, you can just go to 6 and say, will you have this?
Okay, so question is, if you have a global view of the system, could you not have just gone to 6 and say, do you win? All that we have said is, you know, the addresses, which may be IP addresses of all the processes, you don't know whether they are running or not. Okay? Global view doesn't mean you know what the status of the process is. Process could have crashed. I just know that process 6 runs on this IP address and this port number. Whether the process is running is not known. That is why you actually run this algorithm. You say which of all the nodes, which one is still up. That's the one that's going to be the leader. Okay? Yes, question?
How do the rest of the processes come to know if the coordinator has failed?
How do the rest of the processes come to know if the coordinator has failed? Okay, so there are many ways you could do this. Okay, so if the coordinator is actually coordinating some task and you are expecting to get messages from that process, you don't hear from it, you can just declare that the coordinator has failed. So let's say it was clock synchronization. Every so often you contact the time server and say what's the current time. The time server does not respond, you say time server has failed. Let's run a new leader election. So whatever task is being performed by the leader, if you see that the leader is not responding to messages for that task, you can run a leader election.
So is there a specified timeout or number of timeouts?
Right, so you might have to use some timeouts to figure out. Okay. The other way is every so often the leader could send a message saying I'm alive. If you don't hear a message every 30 minutes from your leader saying I'm alive, or you're not directly communicated with the leader, you can declare the leader may be down. Okay? Yes.
This seems like a very non-optimal algorithm. Is it used practically today?
Okay. Question is, it seems very simple. Is it used? So it is very simple. Typically, as I said, you will not use numeric IDs to elect processes. You will actually use other properties like the load on the system or available resources or bandwidth and so on. But this just illustrates how the process works. What metric you use to elect the leader is less important. Here the metric was just ID, but you could have substituted that with load. Right? And you could have said, tell me the load, and figured out which one is the least load.
And that would require a lot of querying.
Okay. So we'll talk about how to do other metrics in just a moment. Okay, yes, question?
So to know whether a process is alive or not, we should be sending some sort of a heartbeat thing, right? Like you said, if we do that, but and in that case, do we have to flood the entire network?
Okay. Question is, if you use heartbeat messages to know whether the leader is alive, do you need to flood the network? So the heartbeat message simply tells you, so first of all, in a distributed system, not every process is going to send heartbeat messages to every other process. That will just be too complicated. So in this case, the only thing you might do is the leader might be sending I am alive or heartbeat messages. Okay, so the only thing you might know is whether the leader is up or not. You might know the addresses of other processes, but you may not be directly communicating with them. So when you need to run a leader election, you would have to explicitly communicate with other nodes to see who is up. Okay, that is why you are going to do this. This is hopefully not going to be frequent. Yes, but you might have to pay the price to actually discover the process with the highest ID, or as I said, least load, or any other metric. At that point, you have to pay that price. But heartbeat messages, you don't have to have order n square communication.
Just one more question. What would happen if can two elections take place simultaneously?
Okay, that's a good question. The question is, can two elections take place simultaneously? Okay, first of all, any process can initiate an election. So two processes more or less at the same time might realize the leader is down and initiate an election. Okay? And it doesn't matter, because if the nodes, group of nodes is static, okay, the same node is going to win. Okay? In fact, you will see that in this recursive case, multiple elections are actually happening. Okay? So you will see 4 started an election, and this caused 5 to start an election, and you will see 6 also has an election. So this is actually happening in any case, okay, because of the recursive nature of the process. So even if there are multiple nodes independently starting an election, you will still end up with the same result, okay, which is that 6 gets elected, and if it's already the leader, it won't change anything. Okay?
I guess if a node is waiting for a response from its higher ID nodes, then it can just discard any future request because it's already sent it to answer this question.
Right. So you could have multiple elections. You will basically, you shouldn't, just for consistency, say I already replied or voted in that election, so I'm not going to vote in this election, because you don't know what might have triggered it. Okay, it might so happen that between the 2 elections something may have gone wrong in the system. So you should just run recursively this algorithm, and if nothing has changed, the same node will get re-elected. Both elections will have the same end result. Okay, so that's fine. What you don't want is 2 elections that are concurrent electing different leaders. Okay, that won't happen if the nodes don't change in the system. Something fails in between, then of course the outcome will be different. Okay, so now with that, yes, your question.
So will the election stop if once the leader is chosen, because the coordinator sends the messages to all the nodes in the system?
Right, so each election will end with a final, the question is, when does the election algorithm stop? Okay, each election will end with the coordinator sending an I1, or which is also called a coordinator message. So that election has ended. If there are other elections in progress, they will proceed, and they will also end with the same result.
So like, since we already have a leader, shouldn't the other election stop?
Right, so the question is, since we already have a leader, shouldn't other elections stop? You could optimize it that the simplest thing is, let each election run to its conclusion. If nothing has changed, only 7 is still the only failed node, you will just repeatedly elect 6. Okay? That may be wasteful, but it's not going to result in any inconsistencies. Okay? So of course, you can make everything more efficient, but here we are more worried about correctness, okay? Which is you want to elect one leader and the highest ID process. Okay? But yeah, efficiency, of course, you could do better when there are multiple elections and so on. Okay? Now it should be clear this has order n square complexity, okay, because every time you will basically contact I minus n minus I nodes higher than you. So the worst case is 0 starts the election, it will send n minus 1 messages or n minus 2, then once will send those messages, 2 will send those messages, so end with order n square messages. Okay? So not very efficient, but still a simple algorithm. So next algorithm we will look at is a ring-based algorithm. In this case, okay, we will also use the same metric, which is to choose the highest ID process, but this algorithm can be very simply modified to choose any other metric. Okay, you can say least loaded node, node with the highest bandwidth, whatever metric you want, okay, you can basically piggyback on the ring algorithm and use for electing a coordinator with those characteristics. Okay? So again, we will make a simple assumption, which is that we have ordered processes 1 through n. Okay? In this case, we will not assume that every process knows the IDs of every other process. The only thing we will say is that processes are ordered in a ring. So process I only needs to know the address of I plus 1 and I minus 1. So you only need to know the addresses of 2 neighbors. Okay? Now, of course, if the neighbors are failed, you will need to discover the neighbor's neighbor, but that's a separate process altogether. Okay, but the point is you may not need to know every node in the system. You might need to know some small subset of neighbors. Okay? So, and we will basically say, now we want to elect the node with the highest ID. And then the way this is going to work is we are going to send or circulate an election message through the ring. Okay, any node can start an election. And the way you do it is, let's say processes circulate clockwise. Okay? So then I will basically send an election message to I plus 1. And every time you receive an election message, you piggyback your ID, okay, saying I am 6. Okay? And then you send that election message to the next node. Okay? And by piggybacking your ID, you're saying I am 11. Okay? So essentially the message will circulate through the ring, and when it comes back to the node that initiated the election, that message will have the list of all nodes that have stuck their IDs on their message, okay, which are all the nodes that are alive. So you simply scan them and pick the one with the highest ID. Okay, and then that is the one that is going to win. Okay, so here is an example that shows you what's happened. Same scenario as before, 7 has crashed. Okay. Nodes are essentially in a ring. In this case, what is being shown is actually there are 2 elections that have started simultaneously. Okay. 5 started an election, okay, by saying let's have an election, it piggybacked its address and so on. Okay. And then essentially 6 will piggyback his address, try to contact 7, which it cannot, then it will just send that message to 0, and then 0 sends it and so on. So you'll see that this is the message is circulated halfway through the ring, and it's collecting IDs of every node that is up. Okay? And here's a second election that is started by 2, which is the same thing is happening. 2 has sent a message to 3, and then 3 has stuck its ID and it's sending it along. Okay? Now both of those messages elections will cause the message to circulate through the ring. Okay, and when it comes back to the originator, okay, meaning that message here comes back to 5, it will have a list of all IDs, okay, that are of processes that are up, and it will simply say 6 is the highest one among them, and you pick 6. Okay. Now this is where you could have said, rather than just putting your ID, add your ID and put your node, okay, or add your ID and put some other metric, and then you can just look at those metrics and say I will pick the least loaded node or some other metric like that. Okay. But for now we are simply going to pick the highest ID process. Okay. And so 5 will then basically figure out 6 is the highest ID process, and 2 will have the same conclusion. Okay. So both elections are going to result in the same outcome, but that doesn't matter. Okay. Just to show you that there could be multiple elections in progress. Okay. Now this will have order n complexity because message is just circulating through a ring. In fact, the message has to circulate twice. The first time to query all the nodes, and then you say 6. So then you pick a leader and then you circulate another message saying here's the new leader. Okay, so essentially you have to send the results of your election to all the nodes. That will also be a message that propagates through the ring. Okay, so 2n minus 1 messages will actually go through the ring. Okay, n minus 1 for the first round, n minus 1 for the second round. Okay? Any questions on this? This is much simpler algorithm. But it does require you to enforce a logical ring topology on whatever your application is. Okay, this could have been a random other application, you're just putting a ring topology on top of it, just for leader election. But you still need to do it. Okay, yes.
What if if it's a large big network, what if 7 crashes by the time or 25 crashes by the time one sees?
Okay, that's a good question. The question is, what happens if it's a large ring and while an election is in process, some other node crashes? Okay, so essentially if the topology of your network is changing during an election, then your election will not result in a consistent outcome. In particular, if you pick 6 and by the time you send 6 saying 6 is the leader, 6 already crashes, then you will again have to keep rerunning the leader election algorithm to get a stable result. Okay? That is true of any election algorithm, not just ring. In any large system, if nodes are actually changing while the election is in progress, the outcome may be inconsistent. Okay? Simply because a newer higher ID process may arrive, or the one that you picked might crash by the time you tell someone. So the assumptions that most of these algorithms make is there will be dynamics in the system, but not during the leader election algorithm. Or if there is, then you can run another leader election algorithm and get a stable result next time. Okay? The worst you will do is you will pick a leader that went down after you chose it. Okay? Or you pick a leader and by the time you announce that 7 came back up. But then you can always run another leader. Okay, next question.
If the 7 is down, how 6 can know it should send message to the 0?
Okay, question is, if 7 is down, how does 6 know that it has to skip 7 and go to 6? Okay? This is true of any ring-based topology. Okay? Essentially, if you want to tolerate failures, you will assume that you have some knowledge of not just your immediate neighbors, but their neighbors' neighbors, and maybe their neighbor's neighbor's neighbor, and so on. So what will happen in this case is 6 will try to send a message saying this message, 5 and 6 to 7. Okay? But since 7 is not responding, maybe you try to establish a socket connection, you get an error. So you say 7 is not responding, so I cannot actually propagate my ring election message to 7, so I'm going to then skip over 7 and just directly talk to its neighbors. Okay? So then you will connect to 0 and send it to 0.
So every process can know the whole topology of the ring.
Right. So question is, do you need to know the whole topology of the ring? In the worst case, if lots of processes crash all at the same time, you might have to actually know a lot more information. Okay? But the simple case is always know your neighbors. Okay? You might need to know the neighbor's neighbor. Okay? And if you assume that only one process crashes at a time, then that's adequate, because the worst that will happen if only one process crashes at a time is your neighbor crash. So if you know your neighbor's neighbor, then you are good. You can still fulfill the requirements of the leader election. So if you assume that up to n nodes crash k nodes crash at the same time, you will at least have to know k neighbors in either direction, because the worst case is those k neighbors in a chain all crashed and you have to skip over them and go to the k plus first one. So that is the level of topology information you need to know, okay? Which is much less than what you need to know for the Boolean algorithm. Okay, there we assume you know everything. Here you need to know some part of your chain, okay? Not necessarily all of it, depending on how many failures you want to tolerate simultaneously. Any other questions? Okay, so that is a ring algorithm. Here is a quick comparison between the two. Okay, so we assumed n processes, okay, and let's assume there's only one election in progress. Okay, the Boolean algorithm, the worst case is the initiator is the node with the lowest ID. In this case, you will have n minus 2 elections at higher ID processes, because this is recursive, you order n square messages. The best case is essentially the node with the one that is actually the highest ID process that's currently up, starts the election, there is no other node to contact, so it declares itself the winner immediately. Okay, so in this case, you just send an I1 message to the remaining one, so n minus 2 message. So depending on who has initiated the election, you will be somewhere in between. Okay, the typical case is order n square messages. Okay, in ring, you always have 2n minus 1 messages. First time you query all the nodes, second time you tell everyone what the results of the election. Okay, linear complexity. Okay, any questions here? Good. So let's talk a little bit about some other scenarios. Okay, so here is you will see if you actually go and look up papers on leader election, there are many different papers that you will find. Yes, you will see leader election in wireless environment. I'll talk a little bit about leader in election in peer-to-peer environments and so on. Okay. So you have an ability to find a leader. Okay. But because you have a wireless network, that you have nodes that are communicating directly with one another, some nodes may not be even in range of other nodes. Okay. So you cannot assume, unlike your bully algorithm, that any node can talk to any other node. Okay, because you cannot simply send a message to all nodes higher than you, simply because some of those nodes may not be in broadcast range of. So you can only communicate with nodes that can receive your wireless message. Okay, so the way you will have to do this in wireless environments is slightly different. Okay, and we are assuming what is called ad hoc network, and nodes are directly communicating with one another, not through a base station. This is not like a Wi-Fi network where you send messages to either a cell tower or an access point and then you get to someone. That's a different scenario. This is just a set of nodes that are directly sending messages in an ad hoc network. In this case, there are some nodes that may not be reachable. Okay? So you have to make other assumptions. But you will assume that the network is connected, which means some nodes might fail, but the rest of the network is connected. You have at least some way to communicate with other nodes. So what happens in this case is 4. In this case, let's say it decides to start an election. So 4 is going to broadcast a message, okay, and then it is going to reach, in this case, 6 and not 4 actually. 4 is actually the metric or the capacity of the node. So A initiates the election. It broadcasts a message, it receives, goes to B and J, and then that will keep going on. Okay, so that's B will broadcast an election message, and will basically it will propagate through the network in the form of an overlay tree. Okay? So essentially, you keep doing this until all the nodes have actually received the message, and then when you send your responses back, you will say, I am such and such node, and this is the metric. In this case, the metric is the spare capacity of each node. Okay, so you will see that F has sent a message saying I have idle capacity 4, D has sent a message saying idle capacity 2. All of that flows back over the tree. Okay? It hits back, it goes back to the source, and then the source can take all of that information and find the node that has the most capacity and declare it the lead. Okay? Again, a form of querying, but you're using a tree-like structure that is constructed on the fly based on which node can actually communicate with which other node, who is in range of wireless nodes. Just a very quick sample to illustrate there are many different ways to do this. In all of these election algorithms, one thing is common. You have to basically initiate an election. Somehow you have to reach all the nodes on the network and figure out what is it that you care about. A node with the highest ID, the node with the most capacity. Get that information and declare that node the leader. Okay, that's basically what's going on in most of these cases. Here is a different example for doing this in peer-to-peer systems. When we talked about Skype, okay, we said at one point Skype had a super peer topology where you had groups of Skype peers that would elect one node as a super peer. Okay? That super peer, and this was to prevent things like flooding, okay? Because if you're flooding the network and there are millions of nodes, that's a lot of messages. So the assumption was super peers will basically flood other super peers, but they will answer for all the nodes within their cluster. Okay, so peers won't actually have to participate in any other protocol, so super peers deal with it. Okay, so there was a requirement that each group of Skype peers would elect the most powerful node within their group to become a super peer. Okay, that node should have adequate processing capacity and adequate network bandwidth. Okay, you should not kill the bandwidth or kill the node by just overloading it. Okay, so that was basically how you did that in Skype. Now you had the same requirement that within each group you will run a leader election algorithm. The metric you will choose would be different in this case. Okay, find a node that is maybe on a wired network. Okay, if you are on a cell phone and you make that phone a super peer, you will kill someone's data allotment. Okay, so you don't want to do things like that. Okay, but you want to be careful saying pick a node that's on a wired network. Pick a node that is reasonably stable where the Skype client is logged in for long periods of time. Okay, because if you come and go, then you have to keep electing new super peers. Okay? So stability, resource availability, they are all important criteria. Okay, so those would be the criteria you use to pick super peers in Skype-like environment. Okay? Now the underlying algorithm you use is not as important. It could be any variant of ring or bully or any of the other variants I alluded to. Okay? In fact, what algorithm Skype super peer used is actually not documented publicly. So nobody really knows what they use, but it would be some variant of this. Okay? But the criteria you would use to pick a super peer is clear. Okay? You want nodes that actually have the ability to take on extra work. Okay? You don't want some other someone on a laptop or on a cell phone, any of those clients to be elected as super. Okay, so essentially, those are all examples of how other systems have also used leader election to achieve some of these goals. Okay? Any questions on this? So I won't go into specific details of electing super peer. It's just an election algorithm underneath. But I just wanted to mention that as one of the scenarios we have encountered in the past where leader election is necessary. Okay? Yes, questions?
So a super peer is like a hierarchy, right?
Yes.
Like one is above the rest.
Yes.
So are there multiple super peer hierarchies? Like a
Sorry.
collection of super peers, like a super peer who is superior to other super peers?
So this was a picture I think I had in lecture 3 or 4, I don't remember the lecture number. So we assume that within each group of peers, okay, you have a cluster group of peers, so you would have to elect one super peer which I have actually shaded here. And then those are the ones that are going to talk to one another. Okay, and you are asking, can you layer another level of hierarchy on top of that?
Is there?
Okay, so in Skype there wasn't, that was the topology. So you basically had overlay network of super peers which would talk to one another, answer queries of who is up, or if when you log in you want to see of your friends list who else is logged in. All of that information was maintained by super peer. It did not have a layer of hierarchy on top of it. If you want to, you could, but that architecture was not
There
used in
would
Skype.
be some functionality for that as well, like the purpose of having another layer.
Right. So you need to have a specific reason to have another layer. But typically when you say peer-to-peer, by definition, you assume all peers are equal. Already you're deviated from that and said some peers are more equal than others, they are super peers. Okay, so if you start making those distinctions, then the peer-to-peer philosophy is no longer in place. Okay, but at least Skype does this. Used to, not anymore. Yes, question.
Super peers in one group, how does super peer in one group know the address of the super peer in another group?
Okay. Question is, how do super peers in one group know the addresses of super peer in other groups? That's a classic P2P question. There's nothing to do with super peer. You could have said, how does any peer in a P2P network know the peer address of any other peer? Most P2P networks have what's called a discovery process, where you can discover the presence of other peers and get to know their addresses and so on. Okay? Super peers will have to run the same kind of discovery process, where it's not like these nodes cannot talk to those nodes, they're just part of a cluster, but you can actually have links going that way, and in that case you can actually discover addresses and so on. Okay? So every P2P network has to deal with that problem. How do you know the node address of any other peer? Okay. Any other questions? Okay, so now with that, let's move on to the next subtopic, which is distributed synchronization. Okay. So this is the problem of implementing a distributed lock. Okay, so far, all of you know what a lock is. So you probably have used it in multi-threaded code and whatnot. Every time you want to access a shared data structure, you guard it with a lock. Okay, you want to acquire the lock before you access that data structure or you enter a critical section, and you release the lock when you are done with it. This is our standard assumption. Okay. Now in a distributed system, okay, that notion of a centralized lock may not work anymore. Yes, let's assume you have n processes that want to access a single file that is stored on some other machine. Okay. So you want to grab a lock on that file. Okay, how do these processes coordinate among themselves to figure out who gets the lock? Okay, so you want to take our notion of a centralized lock and make it distributed which basically means any group of n processes can actually say, get me a lock, and then you have to run a protocol to figure out who wins, and then that process gets to access that resource. Okay? So that's basically what a notion of a distributed lock is. Okay? So you can use that same concept and take semaphores and monitors with the other synchronization primitives and make them distributed as well. Okay? For simplicity, I'm just going to use the notion of a lock and show you how to make it distributed. Okay? First, we'll start with a centralized approach. Okay? Meaning, although it's a distributed lock, we will have a centralized coordinator that's going to manage the lock. The coordinator will be elected using a leader election algorithm. Okay, but there will be still one point of failure, which means the coordinator goes down. Okay, then you cannot actually do any locking operations anymore. Okay, then we will see how to make that decentralized, no coordinator. We'll see how to work on that as well. Okay, so and then we'll look at a ring-based version of a lock, which will be our third technique. Okay, so we're going to look at 3 ways to do distributed locking. Okay, starting with something that is fairly simple, which is centralized mutual exclusion. Centralized mutual exclusion doesn't mean that you have only one process. Okay, that's what we have a traditional lock. What this means is there are n processes, but the how to coordinate locking and unlocking is still being done by a master process. Okay. So the technique is as follows. So we'll assume processes are numbered, okay, 1 through n or 0 through n. Okay, first we run a leader election. And in this case, we'll pick a coordinator. Let's say pick the highest ID process. Okay, we know how to do that already. Okay, so that's our lock manager or the lock coordinator. Okay. Now, if any other process in the system wants to grab a lock, it has to first send a lock message to the coordinator. Okay, so you're going to send a request, and then you have to block until you get a reply saying you have the lock. Okay. No different from any other lock acquire message. All lock acquire messages are blocking. When you do lock acquire, you will block until you have the lock. If the lock is in use, you might block for a long period of time, and when the lock acquire message returns with the success, you know you have the lock. Okay? We will give the same abstraction here. Okay? A lock acquire message is actually going, or a request is going to be a network message to the coordinator. The coordinator is going to hold on to that message until it's your turn to get the lock. At that point, it will say go ahead. Yeah, and then you have the lock. So then you can do whatever you need to do, and then you can then send a lock release message back to the coordinator at a later time. Okay? So essentially that's how things are going to work. And the coordinator message, or rather the coordinator process has to find a way to do some arbitration. If multiple requests come for the lock, it has to basically only let one request win. By definition of the lock, you can only have one process in your critical section at any given time. Okay? Now you can have many different ways to decide who wins. We are going to simply use a first come first serve mechanism. Okay? Request messages will arrive in a queue. If multiple requests arrive in the queue at the same time, the one that arrived first at the head of the queue is going to win. Okay? So that's basically how things are going to work. Here's an example of how this very simple distributed locking framework works. So we have 4 processes, 0 to 3. Okay? We run a leader election, 3 is going to win. It's going to become the lock manager. Okay? For every lock that it manages, it's going to keep a queue. Okay? You can have multiple locks. Every lock will have its own queue. Okay? Now when any process wants to request the lock, it is going to send a request message saying, I request lock X or a lock I. Okay? And it's going to send that request message to the coordinator. That request message is going to arrive in the queue. Okay, if the lock is free, you will simply grant that process the lock. Okay, in this case, when you make a request, the queue is empty, so you will immediately get the lock with an OK message. Okay? At this point, one holds the lock. Okay? If 2 sends a request at this point, saying I want that same lock, okay, you will basically be put in this queue. Okay? Multiple, and then you will basically be blocked. 2 will not have a OK message until the lock is released by 1. So 2 will be blocked waiting for the lock. Exactly how lock messages or a lock request blocks if the lock is in use in a centralized process. Okay, so in this case, 3 will not reply, it simply put that message will be outstanding. When 1 releases the lock, at that point you look in the queue, take the request at the head of the queue, multiple requests will be queued here, take the request at the head and say now you have the lock. So 2 will now continue. Okay? It will enter the critical section, do whatever it needs to do, And when it sends the release message, then you're going to then look at the queue again and do whatever you need to do. Okay? So that's a simple implementation of a distributed locking protocol. You know, this protocol will have many problems, okay? All of which have to do with failures, which you don't see in a centralized process. Because the first thing is coordinator may crash. Okay, so now you have outstanding lock messages that disappear. If you elect a new coordinator, that coordinator has to somehow figure out what was the state of the queue before that lock manager crashed. If you cannot figure that out, then you might have processes like 2 that are just waiting for a reply. The new coordinator does not know that 2 is even blocked, then you will not have a consistency. Okay? That's the first problem. Okay? But let's say that you can figure out by saying, whenever I put something in a queue, I write it onto a file which is on on a disk. So even if the process crashes, I can go read that file and figure out what has happened before the crash. Okay? So you can persist the state of the lock on stable storage, okay? And then you can recover the state of the lock queue if the coordinator crashes. That's actually the easy part. Okay? The harder problem occurs if one of the client process that holding the lock crashes. Okay? Now, in this case, one is holding the lock. Let's say one just crashes. Okay? Now, the coordinator is just waiting for the lock to be released. It is never going to be released. Okay? 2 will block forever. Okay? So you will have a problem. If some process crashes, all other processes that are waiting on that lock will block forever. Okay? You can't do simple things like timeout. You can't say you can only hold the lock for 1 minute and then I'm going to give the lock to someone else. That's not how locks work. Okay? The abstraction of a lock is you want to acquire and release. Okay? Until you can hold it for arbitrary periods until you release. None of that assume that the holder of the lock might crash. Okay? In a multi-threaded process, okay, if your thread has crashed, most likely your process is going down with the thread. Okay, so this problem doesn't arise. Okay, the whole process might crash if there was a bug and the thread crashed. In this case, these are processes on independent machines. They might crash independently of one another. If you happen to hold the lock and crash, you are basically going to hold up the rest of the system. So these are all hard problems to solve. Okay? So if you want to make this really robust, you have to deal with coordinator failures. Okay? Client failures are hard to deal with. Okay? You might not know how to deal with this. Okay? If you can detect the failure of a process. Okay? And should you, if you know that 2 has failed or 1 has failed, one holding the lock and failed, should you forcibly take the lock back? Is that even allowed? Okay? What if one reboots and continues computing from where it left off? You've taken the lock saying 1 crashed, so I don't hear from when I take the lock back. Now that will cause inconsistencies as well. Okay? So these are not easy problems to resolve. You might have to actually look at what your application is willing to tolerate and make some assumptions. And you might have to say, if process is crashed, then I might take the lock. Or you can hold the lock for some period of time, and then if you want to keep the lock, you might have to actually renew the lock. Okay, you might do that. Say, I grant you the lock for 1 minute. Okay, at the end of 1 minute, if you want to hold it, send me a message saying I want to renew my lock. If you don't hear from it, then the lock is gone. Okay? This changes the abstraction of a lock. Okay? We never actually grant the lock for a period of time. But to deal with things like failures, you might have to change how locks work at all, okay, to make it robust to failures and so on. Okay? So depending on what your application is, you might have to make some assumptions to deal with these thorny issues. Okay? So it's not a trivial thing to just take. I mean, this looks straightforward, okay? But when you have failures, none of this will work. Just the bad things will happen, so you want to deal with all that. Okay? Yes.
So here when you say critical section, the definition is that it should be the same code block running in all processes, right?
So question is, if it's a critical section, is it the same code block running in all processes? That is not necessary. It could be. In a distributed setting, that is not necessary. But even in a distributed setting, it could be. Okay? Now, locks are also held for resources. Okay? If you want to modify a file to take a lock, okay, they are widely used in databases. Right? So if you want to modify a table, your query has to get a lock. Any transaction will get a lock before it modifies a table. Okay? That's also an example of why you need a lock. Okay, so what I'm simply saying is the traditional notion of a critical section, which is the same code executed by all the thread, is not necessarily all the reasons you have critical section. You might have them modify the same underlying data structure.
So then, how do you differentiate from, like, if P1 just wants to read something, then it should be given through, and if P2 is writing, then you should differentiate a write and a read. So,
Okay, the question is how, if you are doing different operations on a resource, how do you distinguish between them? Is
Yeah.
that your question? So that depends on how you are using a lock. If you want to, when you modify data structures, okay, you grab a lock regardless of the operation. That's one way you do it. Right? So it doesn't matter whether read or a write. Okay. So you can have two reasons you have a lock. One is you guard a piece of code, that's called a critical section, or you guard a shared data structure. In that case, you might actually have a read or a write, but you still need a lock. Okay? The other way to do it is to actually have what are called read-write locks. In the read-write lock, multiple readers are allowed, but when you have a write, then everything is basically mutually exclusive. Okay? So there's a special kind of a lock called a read-write lock that allows you more concurrency, but let's not go there. For simplicity, we'll assume that whenever you need to make a change to anything, you will grab a lock. Transactions do that well. In a database, when you're trying to update a table or a record, you will grab a lock. Yeah?
Basically, I guess we use semaphores for reads, right? Because we can keep a semaphore count.
Right. So you can use semaphores as well. They can work as a lock. You can also use them to implement read-write locks and so on. Okay, but that's kind of an orthogonal discussion from just saying that you need to grab a lock when you are trying to do any shared operation. Whether the shared operation is executing a shared piece of code or modifying the same data structure across multiple processes, that's still something that needs mutual exclusion. Okay? Okay, so now we will go from this centralized case. So let me talk about properties, okay, and then we'll go to the decentralized. So here, basically, what we have done is we used a centralized coordinator, okay, to handle blocking calls. Okay, we'll say that this protocol is fair, okay, because requests are granted the lock in the order in which they are received. So you are simply queuing them and serving them in first come first served order. No one is getting more favorable treatment than the others. Okay. The protocol is all further more simple because you have only 3 messages in this whole protocol. Okay, a request message to ask for a lock, a grant message that comes from the coordinator saying you have the lock, and a release message that says I give up the lock. Okay, very simple protocol. Okay. But many shortcomings. Single point of failure. The coordinator can become a bottleneck, it can fail. Okay, so then you are basically going to be in trouble. And you have to figure out what happens when the coordinator fails, how do you decide which locks are in use and all of that. Okay? And as I said, if the client process is crashed, that further complicates the problem. Okay? So you might have performance bottlenecks, you might actually have correctness issues if you can't deal with, or deadlock issues rather, if you can't deal with failed client processes. Okay? So those are all things that make this far less than practical. So you might have to put additional mechanisms to deal with those issues. Okay? So here now I'll talk about a different algorithm, okay, one that is decentralized. Okay, so this is going to be voting driven. Okay, there's no coordinator now. Okay, so all processes have to participate in voting to figure out which lock request to grant. If there are multiple lock requests, you are going to use voting to figure out who is going to win. Okay, so essentially we'll assume that there are n replicas. And within each replica, there's a coordinator thread. This is not the same as a global coordinator, but we'll say within each process, you will have an extra thread that is simply going to deal with all these locking requests. Okay, we'll call that the coordinator thread within that process. It's not a single coordinator for the entire system. Okay. And we'll say to acquire a lock, you need a strict majority. Okay, so essentially, you will make a request. Everyone will vote yes or no. You get the lock or not get a lock. The majority say yes, you are going to win. Okay? So what that means is essentially coordinators will now receive, when you make a request, everyone says yes or no, and based on what's going on. So if some other process already has a lock, okay, you would have assumed that to get that lock, you have got majority of the rest to say yes. Okay, so those processes actually know that the lock is in use. So some other process is trying to grab the lock, at least those processes should reply saying, no, the lock is in use. Okay? So essentially what we have done is we have taken whatever the centralized node was doing, which was keeping track of who has the lock, and make every process keep track of it. Okay? So if every process keeps track of who has the lock, then we can deal with failures, because if some nodes go down, okay, so long as the majority agree that whether is the lock in use and whether you should have the lock or not, you're still fine. Is that clear, what I just said? Or not clear? Okay, so essentially we have taken the previous protocol, okay, which is this protocol, and we are going to make every process run the same algorithm. Which means when you request a lock, you ask all the processes, saying, I want the lock. Okay? And we want the majority of the processes to tell you what to do. Okay? So majority of the processes will say, okay, go ahead and have the lock, then you can get the lock. Yeah, if you basically don't get a majority saying you can have the lock, you have to block. Okay? So same thing is now being done by every process. What that does is if some processes crash, that's still okay, because you're not waiting for everyone to tell you have the lock. So long as you have a strict majority, you should be okay. Okay, then you have to reason about why is a strict majority okay. Can two processes actually grab the lock at any given time? Okay. I will claim that cannot happen, because when the first process grabs the lock, a majority of the nodes are actually told it that you can have the lock. So those processes know that the lock is in use. You know, if another process actually asks for the lock, at least those processes know that the lock is in use, so they will not reply yes. Okay, so you cannot grab the lock concurrently the second time. Okay. And we assume that some processes can fail, which is why you need a strict majority. Okay, so long as a strict majority says fine, you can basically proceed. Okay. Now this will actually deal with coordinator crashes. Okay. Because you only need a majority. Okay, you don't have one coordinator process, but it doesn't deal with client crashes. Okay, you still don't know what to do. A process that has held the lock just disappears. Okay, it just crashes, then it basically is holding the lock and it's gone. You can't forcibly take it back. Okay, but the coordinator process problem we have dealt with by saying we'll make every process run that algorithm we saw on the previous slide. Okay, and then we'll make them vote. When you make a request, the majority tell you go ahead, we'll just go ahead. Okay, so that means if some subset are failed, they are not going to tell you what to do. Is that clear?
Can you tell about what is the process for releasing the lock? Like this is how you acquire a lock.
Okay. Process for releasing, so question is what's the process for releasing the lock? Every time the process is the same, you are going to essentially broadcast. Okay, so to request a lock, you broadcast and you wait for at least a majority to tell you go ahead. Okay? To release a lock also you broadcast, saying I have given up the lock. So that you are informing every other process in the system saying I gave up the lock.
So there is a possibility that some node thinks you have the lock while you don't have the lock because it was not a part of the majority subset which allowed you to release it.
Okay. So the question being asked is it possible that there is some process that does not know that you have actually gotten the lock or you have released the lock because it was not part of the majority? That is always a possibility. But so long as you're strict majority, you will not have bad things happen. Okay? You might not know what is the current state because you crashed and came back up. So if the lock was granted in the middle, you will not know what happened. Okay? But so long as your strict majority, you will not have incorrectness. Incorrectness will occur if two processes grab the lock at the same time. That's bad. Okay? I'm going to claim that cannot happen because both of them would need majority vote, and at least some process will be at the intersection of that majority, and that process by definition could not have granted the lock twice. Right? So this is why you need a strict majority. So if you need just a strict majority, then you will never have a case where you do not actually get the lock twice. Now some nodes may not know what is going on because they might crash or they might not respond, but that's okay.
But is there any way for them to know, like to complete, not correct?
Is there a way for them to resync with the rest? Yes, of course there is a way, because once the lock is released, okay, you will know now that the lock is actually no longer in use. Okay, so at least you know that. Now you might not know if there are outstanding requests. Okay? For that you might have to add additional messages asking what happened and so on. Okay, this is the same thing that might happen if you crashed and come back up. you want to resynchronize with the rest, you might say, what's the current state of the lock? If you ask other processes and they tell you what the current state is, you will know. Okay? Yes?
Do you have a potential race condition if nodes are coming and going while the voting is going on, because then the value of M will change as you add or lose nodes?
Okay. The question is, could there be a potential race condition if nodes come and go because the value of N will change? Okay. The assumption, I should have mentioned that there is an assumption, that the number of nodes in the system N is fixed. Okay. A priori. Those are all the nodes that could ever be in the system. And you want a strict majority from that full set. Okay. Nodes can come and go, but that will not change N. The only thing it will change is what subset of N are currently up. Okay, so it's not like a P2P system where you start with 100 nodes and then you have 105 nodes. You will say that there are always N nodes, which is what the system is, and from there you can only shrink. Okay, you will never actually go beyond it. And from that end you need a strict majority. That's the assumption. Otherwise this case you mentioned will actually happen, which is a race condition.
When a process is making a decision of okay or no, it basically is like consulting a local, some kind of a map in its own process, that he's requesting access for shared data structure number X, and currently nobody has it, so it's an okay.
Yes. So what you're asking is, if you want to access a data structure, are you keeping track of what is it?
Yeah.
So the way you are going to do this is, or the way you actually write code for this, any data structure you want to guard, any critical section you want to guard, get its own lock. You're not going to say, I want a lock and I'm going to access this. You will say, I have 10 locks. Lock A that guards this array. Lock B guards this integer. Lock C guards this piece of code. So if you want to access that, you get that lock. Okay, so you can have multiple locks. Okay, and you will basically now have to keep track. Well, you'll have one queue per lock and you'll have a state for each lock. Okay, this doesn't say you'll have only one lock for the whole system. You can have as many locks as you want. Yes, good question.
Two questions. One, if a process crashes, I mean, we still haven't dealt with that if a process crashes, the majority still think it has the lock, and others will keep waiting for it.
Right.
And if we do end up fixing that with, let's say, a timeout block or something, we still not at least have discussed how it will be when it comes back up, will it still have access to the data section.
The question is, or the both questions that are asked are related to client crashes, not coordinator crash. Okay, so what happens if the client that's holding the lock crashes? Okay? Should you take that lock back? And if you take that lock back, then what happens if it reboots and thinks it still has the lock? So that's a thorny problem. There's no right answer for it. Okay, so there are only two ways you can deal with it. You can say clients can crash, but I'll never take the lock back forcibly, because there's always a chance it can reboot and think it has the lock. In that case, there's a potential for a deadlock, okay, because it might crash and actually never come back up. Okay, if it comes back up, it might have the lock and might release it. You might just wait for longer. But if it doesn't come back up, you are in a deadlock. Okay. The other side of it is you can say that if the client crashes, I'll have some maximum timeout, and if it doesn't return the lock by that timeout, I will take the lock back. In that case, you have to assume that if it comes back up, the code actually is written so that it assumes that any lock that was held before is gone. This requires the application programmer to actually write extra code to deal with this scenarios, depending on what the system is giving. So you have one or two cases. You have to deal with a deadlock, or you have to write extra code saying if there is a crash and you went down holding the lock, when you come back up, the lock may not be available anymore. Yes, so you will have to change the semantics of what happens, because the locking abstraction was not designed to deal with failure. The centralized case, we assume that if thread crashes, the whole process crashes, so this question never came up. Okay, you would never had some other threads waiting. Here you have to deal with that. So there is no straightforward generalization. None of them are the right, there is no right or wrong. You have to make some assumption and you are stuck with whatever the implications of the assumption are. Okay? Yes.
Is it not sufficient to make sure that a snapshot of a process never happens during a critical section?
Come again, what?
So if you come back up, you have to restore from some state.
Yes.
Is it not sufficient to make sure that the saving of that state never happens during a critical section. So
Right,
that
so
you're always coming back outside of.
Question is, are you going to not do some things like snapshot during a critical section? So this is not directly related to snapshot. Crashes can occur due to bugs. Okay? Somebody may just forcibly shut down the machine or reboot the machine, and the processes that were running go down and they come back up. Now, if they actually use persistent storage, when they come back up, they might actually think they held the lock and so on. So because this is a library that you're writing, okay, just as you're locking library, when you write the library, you don't know every possible way a programmer would use your library. So you want to give clean semantics, and these are the properties. And if you knew every way you would use it, then you would make those right assumptions, but you don't. Okay, so you might actually have bad cases. Question.
So I'm trying to understand when a coordinator would return no, is it during, is it in this scenario where the process that had a lock would release it, but only half of the half of the processes came to know that it has been released, the other half has not come to know yet, and hence it returns a no? Or is there any other scenario where it might happen?
So question is, when would a coordinator return no? So no essentially means that a lock is in use. Okay, you could have not returned any message at all. Okay, but because this is voting based, okay, you have to basically tally the results of a vote. If you don't reply, I don't know what your vote is. Okay, so rather than blocking like in the previous case, I actually tell you lock is in use by voting no. Okay, so that's the first thing. Now the question is, when do you vote no? You can vote a no if the lock is in use. Okay, so if I know some process holds a lock, you request the lock, my vote is a no, you can't have it. Okay? The question is, when would some other process vote a yes if other processes are voting no? That happens if you do not know the state of the law. Maybe you are not tracking it. Maybe you failed and you came back up. So you don't know the state, so you cast an erroneous vote. Okay? And the assumption is because you are using majority rule, even if some processes are off, they don't know the actual state of the law. So long as the majority know what's the right thing, you should be good. That's the assumption. Okay? So we have 5 minutes. I'm going to talk quickly about one last algorithm, and then we are going to actually stop here. Okay, so here is a different algorithm that's also distributed. Okay, this algorithm uses Lamport's clocks. Okay, so we already talked about Lamport's clocks several classes ago. So essentially what we are going to do is, whenever a process enters a critical section or wants to have a lock, it is going to send a request message to all other processes, and you are going to put a timestamp on that message. This is the Lamport's clock timestamp, okay, which we have seen how to use. Okay. When a process receives a Lamport's clock timestamp, you are essentially going to wait, you are going to send a reply message, okay, if you don't want the lock. So here is basically the process to send a reply. Okay. If you get a request message, some process J, if you don't want the lock yourself, you say, I don't care, you can have the lock. That means you send a reply message. Okay. If you are already in the critical section, you can't send a reply message because you are using the lock in this case. So you just queue the request, don't do anything at all. Okay. And the third case is, I don't own the lock or I don't want the lock, but I know that some other process also wants the lock. So in that case, you compare, or I want to enter the critical section, but I haven't gotten it. You are going to compare your timestamp with the timestamp of the other request message, and the one with the lower timestamp will win, because the lower timestamp will tell us that you asked first. Okay? We are simply using Lamport's clocks to get a global ordering of event, and the only event ordering we want is to say who asked first. Okay? The one that asked first wins. This is the same as I queued them in first come first serve order. And the one that asked first is the head of the queue, that wins. So that queue is being replaced with Lamport's clock. We are comparing, if you are making concurrent requests, we are comparing timestamps, and based on the timestamp, we reason about which of them has asked first, and that's the one that will win. Okay? That's the simple generalization from, rather than using a queue, I basically timestamp my messages and I compare the timestamp to see who is going to win. Okay? The one that has a lower timestamp will win when there is contention for the lock. If there is no contention, then there is no problem. Only one process wants the lock, it will win by definition because no one else wants the lock. Only if multiple processes want the lock, you will compare the timestamp, and the one that actually has the lower one will win. Yes, question.
What is the use of timestamp over here?
What is the use of a timestamp?
Yeah, let's say if we have TS, timestamp I, timestamp J, timestamp K. Let's say, I mean, in orders, let's say timestamp I less than timestamp J less than timestamp K.
Yes.
First, for a node, let's say timestamp K has a write and J has a write. So whenever J has a write, it will be sending a response to a timestamp I. What's the advantage of comparing timestamps and sending? You could always send to everyone, right?
So I don't understand your question. So the question maybe we'll have to rephrase, because you are asking why do we need a timestamp to figure out which. So the point, the scenario where there are two, let's say two scenarios. One scenario is only one process wants the lock. No one else wants the lock. In that case, it says I want the lock. Everyone says go ahead. We don't need the lock. That process wins. There's nothing there. Okay? The other case is where two processes want to ask for the lock more or less at the same time. In that case, one of those two processes has to win. Okay? If the lock is in use, both of those processes have to wait. Okay? But let's say eventually the lock is released, still one of those two processes that asked for it have to be will win. Okay? That will get the lock and the other one will not get it. So our question is which one wins? Okay? Our rule is whoever asked first will win. Okay? That's the same as saying those two processes sent a request to the coordinator queued those messages, the one that's ahead will win. Okay? Same is true here. You want to say who asked first. Then the question is, how do you decide who asked first? All of your request messages are going with, so as you see, the request message saying, I am process K, this is my local timestamp and I made the request. So you're sending a timestamp with the request message. So you simply compare the timestamps. Okay, since you're using Lamport's clocks, it will tell us which of the requests was sent first, and that's the one that will win the lock. So that is the reason we have the timestamp at all, to allow us to reason if there are multiple concurrent request messages, which one was sent first. And that's the one that will actually win.
Exactly what he's asking is if there's a queue, then you can just put things in the queue and do FIFO on it.
Right. So if you have a queue, you don't need timestamp, but there is no queue. You are actually using timestamps to reason about messages.
And also, I think it would be better if the coordinator, if the clients don't send their timestamps because of the clock sync issues, and the coordinator, while accepting those requests, adds its own timestamp to that request where the code is executed.
So the question is, first of all, there may be timestamp issues, so you shouldn't have timestamp, and second is the coordinator should add this timestamp. So neither of those assumptions hold. Okay? First thing is Lamport's clocks don't use real timestamp. The whole point of using Lamport's clock is that you are not using clock synchronization. Okay, Lamport's clock works without any clock synchronization at all. Your real clock may be off by arbitrary times. You are using Lamport's clock to deal with that issue. Okay? Second is this is a distributed algorithm. There is no coordinator. If there was a coordinator, you would not need this. Okay, what should be clear is every request message is sent to everyone else. Okay, if there's a contention, then you use timestamp to resolve that contention. If there's a coordinator, you wouldn't need any of this. You would use the first algorithm we talked about. Okay? So you're dealing with two issues that you have in this case. One is you have no coordinator. Okay? Second is we're assuming there's no clock synchronization. You're not using NTP or anything like that. Yet you want a reason about messages. If clocks were synchronized, you wouldn't need this either. But since you don't have clock synchronization, you're using Lamport's clock to help you synchronize the ordering of messages. Okay? So those are the two properties that you are using. If neither of those two properties hold, then you can do something simpler than this. That's the thing to keep in
It's
mind.
a counter more.
Yes.
More of a counter than a timestamp.
Okay, so we'll stop here. We have run out of time. For those of you who came late, okay, so on Wednesday, after class, I will have special office hours. I usually don't have office hours on Wednesday because we have an exam on Thursday. So if you have any questions about the exam, come see me, okay, during this week's office hours. And also I will post the sample solutions for homework 3. If you are looking at the practice test, have any questions, I'm going to post those solutions also. Okay, so let's stop here.